Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin.
Far beyond the inner planets where sunlight weakens and the solar system thins into a wide and structured emptiness, the environment is defined less by objects than by distances. Here the dominant features are not planets or moons, but fields of motion, shaped by gravity over immense scales. The outer solar system extends past the orbit of Neptune into regions where icy bodies drift on slow paths, and where interstellar space begins to press inward. Temperatures are low, measured in tens of degrees above absolute zero, and matter is sparse. Dust grains, charged particles, and occasional fragments of ice and rock move through a gravitational landscape that is smooth but not simple. In this distant region, gravity from the Sun remains the primary organizing force, though its strength has diminished greatly compared to the inner system. Objects here travel slowly, taking centuries or millennia to complete a single orbit. Their paths are usually predictable, shaped by long-established balances between solar gravity and the faint influence of passing stars or the galactic tide. The galactic tide is the gentle pull exerted by the combined mass of stars and dark matter in the Milky Way, acting over vast distances. It subtly stretches and compresses the outermost reaches of the solar system, influencing the slow movement of distant bodies without abrupt changes. Light in this region is scarce. The Sun appears as a brilliant star rather than a dominating disk, and illumination is faint enough that surfaces reflect very little toward Earth. Objects are detected not by their detail, but by their motion, seen as tiny shifts against a background of distant stars. The background itself is dense, filled with countless points of light that remain fixed over human timescales. Any object moving against this field stands out only through careful comparison of images taken hours or days apart. The space between objects is not entirely empty. It contains a thin plasma of charged particles flowing outward from the Sun, known as the solar wind. By the time it reaches these distances, the solar wind has slowed and weakened, but it still carries magnetic fields and energy. These fields interact with dust and gas, though their effects are usually minor on solid bodies, larger than a few meters across. Beyond a certain distance, the influence of the solar wind gives way to the interstellar medium, a mixture of gas and dust that fills the space between stars. The boundary between these two regimes is broad and variable, shaped by solar activity and the motion of the solar system through the galaxy. Within this environment, most known objects belong to long-established populations. The Kuiper belt contains icy remnants from the formation of the planets, arranged in a flattened disk beyond Neptune. Farther still lies the scattered disk, where objects follow elongated and tilted orbits, influenced by past interactions with giant planets. Beyond that, the Oort cloud is thought to exist as a vast spherical reservoir of icy bodies, extending tens of thousands of astronomical units from the Sun. An astronomical unit is the average distance between Earth and the Sun, written here only in words and understood as a standard scale rather than a precise measure. Bodies from the Oort cloud move slowly and are rarely seen unless disturbed into the inner system. Motion in these regions follows expectations that are well tested. Given an object's position at several moments in time, astronomers can calculate its trajectory using classical mechanics. These calculations assume that gravity is the dominant force and that other influences are negligible. For most distant objects, this assumption holds well. Deviations are usually small, and can be traced to known causes such as past encounters with planets or the gradual effect of the galactic tide. Sudden or unexplained changes are rare, especially when observations are spread over months rather than days. The calm predictability of the outer solar system is one reason it is such a useful laboratory for studying motion. With fewer disturbances, small differences between prediction and observation become easier to detect. However, the same distances that simplify the gravitational environment also make observation difficult. Signals are weak, and measurements carry uncertainties. A slight error in position can translate into large uncertainties in derived speed or direction when objects are very far away. For this reason, astronomers approach early observations with caution, allowing time and repeated measurement to refine their understanding. Against this backdrop, the appearance of any new object is first interpreted conservatively. It is placed within known categories and assumed to behave according to established patterns until evidence suggests otherwise. A faint moving point of light detected far from the Sun is usually considered a distant comet, an asteroid on a long-period orbit, or a fragment from the scattered disk. Its motion is expected to fit within the range defined by gravity alone. Only after careful tracking does its true nature begin to emerge. The vastness of this region also means that time itself behaves differently in practical terms. Changes occur slowly, and patience is essential. An object's path must be traced over weeks or months to reveal meaningful trends. A single night of data provides only a hint, not a conclusion. Astronomers rely on accumulation, layering observation upon observation until a coherent picture forms. This slow process mirrors the environment being studied, where nothing moves quickly and nothing changes without cause. The outer solar system thus sets the stage as a realm of quiet motion and long timescales. It is a place where expectations are grounded in centuries of observation and calculation, and where surprises are uncommon. When they do occur, they stand out not through dramatic display, but through subtle inconsistency. A deviation here is not a sudden turn or burst of speed, but a small, persistent difference between where an object should be and where it is found. Such differences are easy to overlook at first, blending into the background of uncertainty. It is within this calm and sparsely populated environment that the object later designated as 3I Atlas first appears in observational data. At this stage, it is nothing more than a moving point against a fixed star field, located far from the warmth and complexity of the inner planets. The environment around it offers no immediate explanation for unusual behavior, only a framework of well-understood forces. The expectation at the outset is that its motion will conform to this framework, as nearly all distant objects do. Any suggestion otherwise must wait for measurement repetition and careful comparison carried out against the steady and predictable backdrop of the outer solar system. Detection in the outer solar system begins not with the object itself, but with the method used to search for it. Survey telescopes are designed to watch large areas of the sky, repeatedly recording faint points of light and comparing their positions over time. Their purpose is not detailed imaging, but coverage trading resolution for breadth. Each exposure captures millions of stars, galaxies, and noise artifacts, all frozen in place relative to one another. What matters is change. Any point that shifts position between exposures becomes a candidate for further attention. Modern surveys rely on wide-field optical telescopes equipped with large digital detectors. These detectors are arrays of light-sensitive elements that convert incoming photons into electrical signals. The process is mechanical and consistent, governed by well-understood physics. Light from distant objects is focused by mirrors, passes through filters that select specific wavelength ranges and reaches the detector where it is recorded as numerical values. Each value corresponds to brightness at a particular location on the sky. The result is an image that can be stored, compared, and analyzed. The same region of sky is typically imaged multiple times in a single night, and then again on subsequent nights. Software aligns these images, precisely correcting for Earth's rotation and the telescope's motion. Once aligned, the images are subtracted from one another. Stationary sources cancel out, leaving behind signals that represent change. Most of these signals are not real objects. They include cosmic rays striking the detector reflections within the optics, or statistical fluctuations in background light. Automated filters remove many of these false positives, but some remain and require human review. A genuine moving object appears as a point of light that shifts position in a consistent direction and at a consistent rate. The apparent speed depends on the object's true motion and its distance from Earth. Distant objects move slowly across the sky, sometimes by only a fraction of an arcsecond per hour. An arcsecond is a unit of angular measurement equal to 1/3600th of a degree, used here only as a descriptive scale rather than a symbol. Detecting such slow motion requires precise measurement and careful control of error. The asteroid terrestrial impact. Last Alert System is one example of a survey designed for this task. Despite its name, its capabilities extend beyond near-Earth objects. It scans the sky systematically, building a time series of images that can reveal motion even at great distances. When a new moving point is identified, it is assigned a provisional designation and reported to a central database where observations from multiple facilities can be combined. At this stage, the object's nature is unknown. It is defined only by its measured positions and brightness. Initial detection does not imply certainty. The first set of measurements is often sparse, sometimes limited to a handful of positions over a short time span. From these, astronomers estimate a preliminary trajectory. This estimate is crude, constrained more by assumption than by data. It assumes a simple gravitational path and assigns a range of possible orbits that could produce the observed motion. The range is often wide, reflecting the uncertainty inherent in limited information. Brightness plays a role in detection, but is an unreliable indicator of size or distance. A small object nearby can appear as bright as a large object far away. Surface properties also matter. An object with a reflective surface returns more light than a darker one of the same size. Surveys measure brightness in standardized bands of wavelength, allowing comparisons between observations, but interpretation remains cautious. At this stage, brightness is treated as a clue rather than a conclusion. Once a candidate is flagged, follow-up observations become important. Other telescopes are tasked with observing the same region to confirm the detection and extend the observation arc. An observation arc is the span of time over which positions are measured. A longer arc reduces uncertainty and allows more reliable calculations. Coordination between observatories increases coverage and reduces the chance that an object will be lost against the background of stars. Timing is critical. Distant objects move slowly, but Earth's own motion introduces apparent shifts known as parallax. As Earth orbits the Sun, nearby objects appear to move against the distant background. This effect helps determine distance, but also complicates early measurements. Survey software accounts for Earth's motion, but residual effects can remain until enough data are collected. The balance between parallax and true motion must be resolved before confident conclusions can be drawn. Detection pipelines are built to handle vast amounts of data automatically. Each night they process thousands of images, flagging candidates and discarding most. The criteria used are conservative by design. It is preferable to miss a marginal object than to flood the system with false detections. As a result, some objects are detected later than they might be, only becoming visible when their motion or brightness crosses a threshold. This delay does not reflect sudden appearance, but gradual accumulation of evidence. For the object later known as 3i Atlas detection follows this standard path. It emerges from the data as a faint moving point, consistent enough to survive automated filtering and interesting enough to warrant attention. At this moment it is not considered unusual. Its motion falls within the broad range allowed by preliminary models, and its brightness does not immediately distinguish it from countless other distant bodies. It is catalogued, tracked and scheduled for further observation. The role of the survey telescope ends here in a practical sense. It has done its job by identifying motion and providing initial measurements. From this point onward, analysis becomes more focused. The raw detections are passed to specialists who refine the measurements, correct for known biases, and integrate new data as it arrives. What begins as a technical process of image comparison gradually becomes an exercise in interpretation guided by physics and constrained by uncertainty. Detection, therefore, is not a single moment but a process. It unfolds through repeated observation, careful filtering, and incremental confirmation. Each step reduces ambiguity but never eliminates it entirely. The object remains defined by numbers rather than narrative, by coordinates and brightness values rather than by physical description. Only later, as measurements accumulate, does its motion begin to suggest patterns that invite closer scrutiny. For now, within the context of survey detection 3, I-Atlas is simply one more point of light moving quietly through a well-mapped sky, recorded faithfully by instruments designed to notice change without judgment. Once detection is confirmed and additional observations are scheduled, attention turns to the careful measurement of motion. Motion is not observed directly, but inferred from changes in position over time. Each recorded position is a coordinate on the sky defined relative to a fixed reference frame of distant stars whose apparent positions do not change on human timescales. By comparing these coordinates across multiple observations, astronomers determine how far and in what direction the object has moved. This process appears straightforward, yet it depends on precision at every step, because the movements involved are extremely small. Each positional measurement carries uncertainty. Light arriving from a distant object is faint and spread across several detector elements, creating a blurred point rather than a sharp dot. Atmospheric conditions, even at high-quality observing sites, introduce subtle distortions. The optics of the telescope and the response of the detector add their own small effects. These influences are well characterized and corrected where possible, but they cannot be eliminated entirely. The final position assigned to an object is therefore a best estimate rather than an exact point. To calculate motion positions are combined with precise timestamps. Timekeeping is critical. Observatories synchronize their clocks using atomic standards, ensuring that the moment of each exposure is known to within fractions of a second. Even so, when objects move slowly, small timing errors can influence derived speeds. The calculations treat time and position together, converting angular movement on the sky into linear motion through space once distance is estimated. Distance is the most challenging parameter to constrain at this stage. For nearby objects, parallax provides a clear signal. For distant ones, parallax is small and difficult to measure. Early estimates rely on assumptions about the object's orbit. These assumptions are grounded in experience based on the behavior of known populations. An object detected far from the Sun is initially assumed to follow a bound orbit unless evidence suggests otherwise. Using this assumption, astronomers generate a family of possible orbits that fit the observed positions within their uncertainties. Speed is derived from how quickly the object's position changes. Direction is determined by the orientation of this change relative to the reference frame. Together, these define the object's apparent motion. Apparent motion is not the same as true motion through space. It includes contributions from Earth's movement, the object's own trajectory, and the geometry of observation. Correcting for these effects requires a model of the solar system that accounts for the positions and motions of major bodies at the time of observation. The initial motion calculated for 3I Atlas appears unremarkable. Its apparent speed is low, consistent with the distant object moving under solar gravity. Its direction aligns with paths commonly seen among long-period bodies approaching from the outer solar system. Within the limits of early data, it fits comfortably among known categories. The numbers, though uncertain, do not yet suggest anything unusual. As more data points are added, the calculation is repeated. Each new position refines the estimates, narrowing the range of possible orbits. Statistical methods are used to weigh measurements according to their quality. Observations taken under good conditions with well-calibrated instruments carry more influence than marginal data. Over time, a preferred solution emerges representing the orbit that best fits all available measurements. This refinement process reveals subtle trends. Small differences between predicted and observed positions persist, even as uncertainties shrink. At first, these differences fall within expected margins. Measurement noise can produce patterns that appear systematic but are not. Astronomers are trained to distrust early anomalies, especially when dealing with faint objects at great distances. Patience and repetition are essential. Motion is often expressed in terms of velocity components. One component describes movement toward or away from the Sun, another describes sideways motion around it. Together they define the object's path. Changes in these components over time indicate acceleration. Under gravity alone, acceleration follows a predictable pattern, determined by distance from the Sun. Deviations from this pattern attract attention only when they are consistent and exceed known sources of error. For 3I Atlas, repeated measurements begin to suggest such consistency. The object's positions, when compared against predictions based on a purely gravitational model, show a small but persistent offset. The offset does not grow randomly, but follows a direction that implies a slight difference in acceleration. At this stage, the difference is described cautiously. It is noted as a residual, a leftover after known effects are accounted for. Residuals are common and often disappear as models improve. Calculating these residuals requires careful bookkeeping. Every known influence is included: gravitational forces from the Sun and planets' relativistic corrections that become relevant at high precision, and the effect of Earth's motion. Each correction is based on established physics and tested methods. What remains after these are applied is examined closely. If it shows structure rather than randomness, it may point to missing factors. Brightness measurements are sometimes used alongside motion to infer physical behavior. Changes in brightness can indicate rotation or activity, which in turn can affect motion through non-gravitational forces. At this stage, 3I Atlas shows no dramatic variation in brightness. Its light curve, a record of brightness over time, is relatively flat within measurement limits. This absence of obvious activity reinforces the initial assumption of a passive body moving under gravity alone. Despite this, the numbers do not settle completely. Each new observation slightly adjusts the calculated orbit, but the same small discrepancy remains. It is not large enough to demand explanation, yet it is persistent enough to be noted. Astronomers document it carefully, resisting the temptation to interpret it prematurely. Experience shows that early anomalies often fade with better data. The process of measuring motion is iterative and conservative. It advances step by step, guided by data rather than expectation. For most objects, this process converges quickly on a stable solution. For 3I, Atlas convergence is slower. The orbit tightens, uncertainties shrink, but the residuals remain. They are small in absolute terms, representing tiny fractions of the object's total motion, yet they are larger than expected given the quality of the data. At this point, the focus remains on measurement rather than explanation. The role is to establish what the object is doing, not why. The numbers are checked, rechecked, and compared across independent datasets. Alternative reductions are performed to rule out processing artifacts. Different teams apply different methods seeking consistency. Agreement between methods strengthens confidence that the measured motion reflects reality rather than error. Through this careful accumulation of measurements, the motion of 3I Atlas becomes increasingly well defined. It is still described in the language of coordinates, velocities, and uncertainties devoid of narrative or implication. Yet within these numbers lies the first hint that its path may not align perfectly with expectation. This hint is subtle, embedded in decimal places and residual plots, visible only to those who examine the data closely. For now, it remains a technical detail noted without emphasis, awaiting further refinement before any broader significance is considered. To understand why a deviation matters, astronomers rely on a clear picture of what motion is expected to look like in the first place. Small bodies in the solar system follow paths governed primarily by gravity. This behavior is described by classical mechanics, which predicts how an object moves when influenced by the mass of the Sun and the planets. These predictions have been tested across centuries, from the motions of planets to the trajectories of distant comets. For objects far from the Sun, the rules are especially clean. With few nearby disturbances, gravity produces smooth, continuous paths that change only gradually. In the outer solar system, the expected path of a small body depends mainly on its distance from the Sun and its initial velocity. If its speed is below a certain threshold, it remains bound, following an elongated orbit that eventually brings it closer to the Sun before sending it back outward. If its speed exceeds that threshold, it follows a hyperbolic path and escapes the solar system entirely. This threshold is known as the escape velocity, which decreases with distance from the Sun. At great distances, the difference between a bound and unbound path becomes subtle, detectable only through careful measurement. Most distant objects detected by surveys fall into the bound category. Their orbits are long and slow, often tilted relative to the plane of the planets. These inclinations reflect their origin in reservoirs like the scattered disk or the distant cloud of icy bodies surrounding the solar system. Despite their variety, their motion shares common features. Acceleration toward the Sun increases gradually as they approach and decreases as they move away. The direction of motion changes smoothly with no sudden shifts unless a close encounter with a planet occurs. Mathematical models describe these paths using a small set of parameters. These include the shape of the orbit, its orientation in space, and the timing of the object's closest approach to the Sun. Once these parameters are determined, the object's position at any given time can be predicted with high accuracy. For well-observed objects, predictions can remain reliable over decades or longer. When predictions fail, the cause is usually traceable to an incomplete model or an unaccounted influence. Non-gravitational effects are considered only when necessary. For comets, the most common source of such effect is outgassing. As a comet approaches, the sun ices on its surface warm and sublimate, releasing gas. This gas carries momentum, producing a small thrust that alters the comet's motion. The effect is usually strongest near the sun, where heating is greatest, and it diminishes rapidly with distance. In the outer solar system, where temperatures remain extremely low, outgassing is expected to be weak or absent. Radiation pressure from sunlight is another possible influence. Photons carry momentum, and when they strike an object, they exert a force. This force is significant only for very small or very low-mass objects such as dust grains. For bodies tens or hundreds of meters across, radiation pressure is negligible compared to gravity, especially at large distances from the sun. Models therefore include it only for specific cases. Gravitational perturbations from planets can also alter paths. A close pass by a giant planet can change an object's orbit, dramatically redirecting it inward or outward. These encounters are well understood and predictable when the positions of planets are known. In the outer solar system, far from planetary orbits, such encounters are rare. The background gravitational field is smooth dominated by the sun, with gentle contributions from the planets acting at a distance. Because of this predictability, astronomers have strong expectations for how newly detected objects should behave once their basic orbit is established. Deviations are evaluated relative to these expectations. A small mismatch between prediction and observation is not immediately alarming. Measurement errors, unmodeled influences, or incomplete data can all produce apparent discrepancies. What matters is persistence. A deviation that remains after repeated observation and refinement demands closer attention. For 3i Atlas, the expected path is calculated using standard assumptions. Its initial measurements place it on a trajectory that resembles those of long-period objects arriving from the outskirts of the solar system. The predicted acceleration follows the familiar inverse relationship, with distance weakening smoothly as the object moves outward. When this model is applied, most observations align well, reinforcing confidence in the overall approach. However, when residuals are examined over time, they do not behave as expected. In a typical case, residuals scatter randomly around zero, reflecting noise rather than structure. Here they show a slight systematic trend. The object appears consistently ahead of or behind its predicted position by a small amount depending on the direction of measurement. The size of this offset is small, measured in tiny fractions of an arc-second, yet it persists across multiple observing sessions and independent datasets. Within the framework of expected motion, such persistence narrows the range of explanations. If gravity alone were responsible, adjusting the orbit parameters should remove the discrepancy. This adjustment is attempted repeatedly. The orbit is recalculated using different fitting methods, weighting schemes, and subsets of data. Each recalculation improves the fit in some respects, yet the same pattern remains. The object's motion is close to expected, but not perfectly so. At this stage, astronomers consider whether the expectations themselves are complete. The gravitational model includes the Sun and all major planets, whose positions and masses are known with high precision. It also includes smaller corrections, such as the relativistic effects predicted by general relativity, which become relevant at high accuracy. These effects are well tested and cannot easily account for the observed trend. Their magnitude and direction are known, and they do not match the pattern seen. The environment of the outer solar system offers few additional forces. There is no dense medium to provide drag. The solar wind is weak and its pressure on a solid body of this size is minimal. Magnetic effects require interaction with charged material, which is unlikely for an inert object at low temperatures. Each possibility is examined and found insufficient to explain the magnitude of the residuals. Expectation therefore becomes a benchmark rather than an answer. The expected behavior defines the baseline against which all observations are compared. For 3I Atlas, the baseline is solid and well established. The object's motion nearly follows it, yet not entirely. This near agreement is what makes the discrepancy interesting. If the motion were wildly different, error would be the first suspicion. Here the difference is subtle, embedded within otherwise normal behavior. Such situations are familiar in astronomy. Many past cases of apparent deviation have been resolved through improved data or refined models. Some have led to new understanding, such as the recognition of non-gravitational forces acting on comets. Others have faded as artifacts of early measurement. The discipline has learned to wait to let evidence accumulate before drawing conclusions. In the context of expected paths 3, I-Atlas occupies an ambiguous position. It behaves largely as predicted for a distant small body, yet it does not conform perfectly. The expectations are clear, the models are mature and the environment is simple. This clarity sharpens attention on the remaining difference. It is not yet framed as a mystery, only as an inconsistency. The role of this stage is to establish firmly what should happen under known physics, so that any departure from it can be recognized without exaggeration. By the end of this phase, the expected motion is defined with confidence. The object's observed path is mapped against it in detail. The two align closely but not exactly. The numbers that describe this alignment are precise, repeatable, and increasingly difficult to dismiss as noise. The groundwork is laid for examining the discrepancy itself not as a challenge to established rules, but as a test of whether all relevant factors have been properly accounted for. The point at which deviation is recognized is not marked by a single observation but by accumulation. It emerges gradually as measurements continue to align imperfectly with expectation. Each new data point is added to the existing record and compared against the predicted path. For a time, the differences appear modest and within tolerance. They are recorded, acknowledged, and set aside as the orbit is refined. Only when the same pattern persists does attention shift from routine adjustment to closer inspection. Deviation is defined here in a narrow technical sense. It refers to a consistent difference between observed positions and those calculated from a model that includes all known forces. The difference is not dramatic. It does not involve sudden changes in direction or speed. Instead, it appears as a steady offset, small in magnitude but coherent in form. The object is repeatedly found slightly away from where it should be given the time in the established model. Recognizing such a deviation requires stability in the data. Early observations are often too sparse or uncertain to support this conclusion. In the case of 3I Atlas, the observation arc lengthens enough to reduce ambiguity. Measurements from different nights taken with different instruments converge on the same result. The uncertainties shrink and the residuals, rather than dispersing, settle into a recognizable pattern. At first, the possibility of systematic error is examined. Survey telescopes and follow-up instruments have known biases. Calibration errors, optical distortions, and atmospheric effects can all shift measured positions in subtle ways. These effects are usually well characterized, but their influence must be reassessed whenever unexpected behavior appears. Independent reductions of the same raw data are performed using different software pipelines and assumptions. The resulting positions are compared. Agreement across methods strengthens confidence that the measurements reflect the object's true motion. Another possibility is catalog error in the reference stars used for alignment. Positions of background stars are taken from large astrometric catalogs, which are updated regularly as measurements improve. Small errors in these catalogs can propagate into object positions. Cross-checks against alternative catalogs help identify such issues. For 3i Atlas, these checks do not eliminate the discrepancy. The same offset remains regardless of the reference frame used. Timing errors are also considered. Even a small misalignment between recorded exposure times and actual observation moments can affect calculated motion. Observatories maintain precise clocks, but verification is essential. Logs are reviewed and timing systems are tested. No anomalies are found that could account for the observed pattern. As instrumental explanations are exhausted, the deviation takes on a clearer definition. It is not a single number, but a trend. Over time, the object appears to drift relative to its predicted position in a way that suggests a small difference in acceleration. The direction of this difference is consistent, indicating that it is not random noise. Its magnitude is small, representing a tiny fraction of the dominant gravitational acceleration from the Sun, yet it is measurable. This recognition does not lead immediately to interpretation. The discipline requires restraint. Deviations have appeared before in early data, only to vanish with further observation. The process therefore emphasizes confirmation. Additional observations are scheduled, extending the arc and sampling different geometries as Earth moves along its orbit. Changes in viewing angle can help separate true motion from projection effects. As the geometry evolves, the same pattern persists. The language used to describe the situation remains cautious. The term deviation is preferred over anomaly. An anomaly implies unexpected behavior, whereas deviation simply denotes difference. At this stage, the difference is established, but its cause is not addressed. The numbers do not add up in the sense that they do not reconcile fully with the simplest model, yet they do not contradict established physics outright. One aspect that draws attention is the distance at which the deviation is observed. The object is far from the Sun, where thermal effects are minimal, and activity is not expected. Non-gravitational forces associated with outgassing typically become apparent closer in when solar heating increases. Observing a deviation at this distance narrows the range of plausible explanations, but it does not eliminate them. It only emphasizes the need for careful accounting. The object's brightness remains steady within measurement limits. No extended features such as a coma or tail are detected. This lack of visible activity complicates interpretation but does not resolve it. Activity can occur at levels below detectability, producing forces that are small yet cumulative. The absence of evidence is not taken as evidence of absence, only as a constraint. As the deviation becomes established, it is quantified. Its magnitude and direction are expressed numerically with associated uncertainties. These values are compared against known effects. The gravitational pull of known planets cannot account for it. The influence of distant massive objects is considered but found insufficient within reasonable bounds. Each comparison reinforces the conclusion that the deviation is real within the limits of current data. This stage marks a transition in focus. The work shifts from measurement to diagnosis. The goal remains descriptive rather than explanatory. The question is not why the object deviates, but how the deviation behaves over time. Does it grow, diminish, or remain constant? Does it align with the object's velocity or point in a fixed direction? These characteristics provide clues without committing to interpretation. Tracking over additional weeks reveals that the deviation evolves smoothly. It does not fluctuate erratically. This smoothness suggests a continuous influence rather than sporadic events. It also argues against random measurement error. Random errors would produce scatter, not coherence. The smooth evolution of the offset strengthens the case for a persistent underlying cause. Despite this, caution remains. The solar system has a history of apparent discrepancies that resolve themselves through improved understanding of existing effects. The discovery of Neptune arose from deviations in Uranus's orbit, yet in that case the deviations were large and systematic. Here the scale is much smaller. The numbers involved are subtle, demanding humility in interpretation. Within the research community, the deviation is shared as a technical note rather than a headline. Colleagues are invited to examine the data, apply independent analyses, and attempt to reproduce the result. This process is slow and methodical. Consensus emerges not through assertion but through repeated confirmation. For 3i Atlas, the discovery of deviation is therefore not a moment of revelation but a state of recognition. It is the point at which the data no longer fit comfortably within expectation, yet do not break it. The object continues along a path that is mostly understood, carrying with it a small discrepancy that refuses to disappear. This discrepancy is recorded faithfully, neither magnified nor dismissed. By the end of this phase, the existence of a deviation is accepted as a working fact. Its presence is incorporated into ongoing analysis, shaping subsequent modelling efforts. The numbers that describe the object's motion are now accompanied by a note of caution, indicating that a simple gravitational model does not fully account for observed behaviour. The significance of this finding remains open, bounded by data and tempered by experience. The discovery lies not in surprise, but in the careful acknowledgement that the motion of 3i Atlas, while largely predictable, contains a small but persistent difference that invites further scrutiny. Once a deviation is accepted as persistent, the next step is to refine the orbit with greater care. Orbit refinement is the process by which initial approximate trajectories are replaced with increasingly precise descriptions of motion. It does not introduce new physics. Instead, it extracts the maximum information from existing observations, reducing uncertainty and clarifying which aspects of the motion are robust. This stage is technical, methodical, and largely invisible outside specialist circles. Yet it is essential for understanding whether a deviation reflects reality or incomplete modelling. An orbit is defined by a set of parameters that describe the size, shape, and orientation of the path, as well as the object's position along it at a given time. Early in an object's discovery, these parameters are poorly constrained. As observations accumulate, the parameter space narrows. Refinement involves adjusting these parameters so that the calculated positions match the observed ones as closely as possible within their uncertainties. The quality of a fit is evaluated statistically using measures that quantify how well the model reproduces the data. For 3i Atlas, refinement begins with the standard gravitational model. This model includes the Sun as the dominant mass and incorporates the gravitational influence of all major planets. Their positions are known with high precision, derived from long-term tracking and spacecraft navigation. These planetary ephemerids provide a stable foundation for calculating gravitational forces at any time. The refinement process integrates the object's equations of motion forward and backward in time, comparing predicted positions with observations at each step. Refinement is iterative. Initial parameters are adjusted slightly. The motion is recalculated and the resulting positions are compared with the data. Differences guide the next adjustment. Over many iterations, the solution converges toward a minimum where further adjustments no longer improve the fit. This minimum represents the best fitting orbit under the assumptions of the model. For most objects, convergence is straightforward. For 3, I-Atlas convergence occurs, but the residuals do not vanish. The persistence of residuals prompts a closer look at how data are weighted. Not all observations are equal. Some are taken under better conditions with higher signal-to-noise ratios and more reliable calibration. Others are marginal, affected by poor weather or low elevation above the horizon. Refinement algorithms assign weights to each observation, giving greater influence to higher quality data. Adjusting these weights can change the outcome of the fit. Multiple weighting schemes are tested to assess sensitivity. Across these tests, the refined orbit remains stable. The overall shape and orientation of the path change little, and the deviation remains. This stability suggests that the discrepancy is not driven by a few problematic data points, but is distributed across the data set. Removing individual observations or subsets does not eliminate it. The deviation appears embedded in the object's motion rather than in isolated measurements. Refinement also explores the possibility of alternative orbital classes. Bound and unbound solutions are compared. A bound orbit implies that the object is gravitationally tied to the Sun, while an unbound orbit implies passage through the solar system from interstellar space. Early estimates may allow both possibilities. As refinement proceeds, one becomes favored based on how well it fits the data. For 3, I-Atlas, the refined solutions indicate a trajectory near the boundary between these classes. This proximity increases sensitivity to small forces. A slight additional acceleration can shift the classification, making precise refinement crucial. Time coverage plays an important role. Observations taken at different points along Earth's orbit provide varying perspectives, helping to disentangle distance and velocity. As Earth moves, parallax effects change, offering leverage to constrain the object's three-dimensional motion. Incorporating these observations tightens constraints on distance and speed, reducing degeneracy between parameters. For 3, I-Atlas, this expanded geometry improves confidence in the refined orbit without resolving the deviation. Refinement also accounts for subtle effects that become relevant at high precision. These include relativistic corrections to Newtonian gravity, which are small but measurable for accurate tracking. They're applied consistently following established formulations. Their inclusion improves overall fit slightly, but does not alter the pattern of residuals. This outcome is expected. The magnitude and direction of relativistic effects are well known and do not match the observed discrepancy. The refined orbit is then propagated forward and backward in time to test its consistency. Backward propagation estimates where the object came from, while forward propagation predicts future positions. If the refined model is correct, it should match past observations and align with new ones as they are collected. For 3, I-Atlas forward predictions based on the refined orbit consistently miss observed positions by the same small amount, reinforcing the conclusion that the model is incomplete rather than the data. Throughout refinement, the emphasis remains on discipline and restraint. Refinement does not seek to explain the deviation, it seeks to characterize it precisely. The refined orbit defines the baseline against which any additional effects must be measured. Without this, baseline interpretation would rest on shifting ground. Precision is therefore valued over novelty. Refinement also clarifies uncertainties. Each parameter carries an associated range that reflects remaining ambiguity. These ranges shrink as data accumulate. For 3i, Atlas uncertainties decrease steadily, yet the deviation remains larger than the combined uncertainties. This relationship is critical. It demonstrates that the discrepancy is not simply an artifact of limited precision, but exceeds what random variation would produce. As refinement reaches maturity, the refined orbit is shared with the wider community. Other researchers use it as a starting point for independent analyses. Some attempt alternative fitting techniques. Others test sensitivity to assumptions about planetary masses or ephemerides. Agreement across these efforts builds confidence that the refined orbit represents the object's true motion as closely as current data allow. The refined orbit also serves practical purposes. It enables accurate pointing for follow-up observations, ensuring that telescopes are directed to the correct region of sky. It informs predictions of brightness and visibility. It guides decisions about resource allocation, determining whether continued tracking is warranted. For 3i Atlas, the refined orbit justifies continued observation precisely because of the unresolved deviation. By the end of this phase, the object's path through space is described with clarity and confidence. The refinement process has done all that can be done within the framework of known forces. The orbit is precise, stable, and reproducible. Yet it does not fully reconcile observation with prediction. The deviation is now defined not as a vague anomaly, but as a quantified difference between a refined gravitational model and reality. This outcome sets the stage for the next layer of analysis. With the orbit refined and uncertainties minimized, attention can turn to potential influences beyond simple gravity. The refined model provides the reference against which such influences are tested. Without this careful groundwork, any discussion of additional forces would be premature. The refinement of the orbit does not resolve the discrepancy, but it transforms it into a clear and measurable feature of 3i Atlas's motion, ready to be examined in detail under increasingly focused scrutiny. With the orbit refined as far as current data allow, attention turns to the role of uncertainty. Uncertainty is not an admission of ignorance, but a quantified description of confidence. Every measurement carries limits set by instruments, environment, and method. Understanding these limits is essential because a deviation is meaningful only if it exceeds what uncertainty can reasonably explain. This stage therefore examines not the object itself, but the reliability of the numbers used to describe it. Astrometric uncertainty begins at the detector. Light from a distant object is faint and arrives mixed with background noise from the sky, the instrument and the detector electronics. The recorded signal represents an average over the exposure time during which the object continues to move slightly. The resulting image spreads the light across several pixels, producing a centroid whose exact location must be estimated. The precision of this estimate depends on brightness background level and the optical quality of the system. For faint objects, the uncertainty can be significant relative to the motion being measured. Atmospheric effects add another layer. Turbulence in Earth's atmosphere causes starlight to shimmer, a phenomenon known as seeing. This blurring varies from moment to moment and across the field of view. Adaptive optics can correct for some of these effects, but wide-field survey telescopes generally operate without such correction. Instead, they rely on statistical averaging and calibration. Residual atmospheric distortion contributes to positional uncertainty, in ways that are difficult to model perfectly. Instrumental factors are also considered. Telescopes flex slightly as they move, and temperature changes can alter optical alignment. Detectors may exhibit subtle non-uniformities in response. Calibration frames correct for many of these effects, yet small residuals remain. These are usually stable over time and can be characterized, but their influence must be included in uncertainty estimates. For 3I atlas data from multiple instruments with different characteristics helps separate object behavior from instrument-specific effects. Time uncertainty, though small, is included as well. Precise timing ensures that positions are associated with the correct moment in the object's motion. Atomic clocks and global time standards provide high accuracy, but practical systems involve layers of hardware and software that can introduce delays. These delays are typically measured and corrected. Remaining timing uncertainty is small compared to positional uncertainty, but is still accounted for in high-precision work. Once individual measurement uncertainties are established, they are propagated through the orbit determination process. This propagation uses statistical methods to estimate how uncertainties in input data affect uncertainties in derived parameters. The result is a covariance matrix that describes not only the uncertainty in each parameter, but also how uncertainties are correlated. For example, uncertainty in distance may correlate with uncertainty in velocity. Understanding these correlations is crucial when evaluating deviations. Random uncertainty produces scatter. If measurement errors were the sole source of discrepancy, residuals would fluctuate around zero without a preferred direction. Their distribution would resemble noise with positive and negative values appearing equally. Systematic uncertainty, by contrast, can produce coherent patterns. Distinguishing between these requires careful analysis. Independent data sets, different instruments, and varied observing conditions provide opportunities to test whether a pattern persists across contexts. For 3I atlas uncertainty analysis shows that individual measurements have uncertainties consistent with expectations for an object of its brightness and distance. When these uncertainties are combined, the predicted range of positions overlaps strongly with observations, yet not completely. The observed residuals fall outside the central region expected from random error alone. Their magnitude exceeds the combined uncertainty envelope, and their coherence suggests a systematic component. One common approach is to inflate uncertainties artificially to see whether the deviation can be absorbed. This conservative step assumes that uncertainties have been underestimated. By increasing them, the model tests whether the discrepancy becomes statistically insignificant. For 3I atlas, even generous inflation does not fully reconcile prediction and observation. The deviation remains larger than the expanded uncertainty range, indicating that underestimation alone is unlikely to be the cause. Another test involves examining uncertainty as a function of time and geometry. If residuals correlate with observing conditions such as low elevation or poor seeing, they may reflect unmodeled atmospheric effects. If they correlate with specific instruments, calibration issues may be implicated. Analysis shows that the deviation appears across different conditions and instruments, weakening the case for a localized source of error. Uncertainty in planetary ephemerides is also considered. The positions and masses of major planets are known with high precision, but small uncertainties remain. These uncertainties propagate into gravitational calculations. However, their magnitude and structure are well characterized and are too small to account for the observed deviation. Adjusting planetary parameters within their uncertainty ranges produces changes far smaller than required. Catalogue uncertainties in reference stars are examined again in this context. Modern astrometric catalogues provide positions and proper motions with high accuracy, yet residual errors exist. These errors can introduce correlated shifts if an object is measured against the same local star field repeatedly. Cross-referencing multiple catalogues and examining residuals relative to different reference frames help assess this possibility. The deviation persists regardless of catalogue choice. Uncertainty analysis also considers the possibility of unrecognized biases in data processing. Automated pipelines apply thresholds and filters that may influence centroid estimation. Alternative processing approaches are applied to subsets of the data using different algorithms and assumptions. The resulting positions differ slightly as expected, but the overall pattern remains unchanged. This robustness strengthens confidence that the deviation is not a processing artifact. At this stage, uncertainty is no longer treated as a blanket explanation, but as a quantified boundary. The analysis establishes what uncertainty can and cannot explain. It demonstrates that while uncertainties are present and significant, they are insufficient to account for the full discrepancy. This conclusion does not imply certainty about the cause of deviation, only about its statistical reality within current limits. The careful treatment of uncertainty serves a broader purpose. It prevents overinterpretation. By explicitly defining confidence limits, it constrains speculation and keeps analysis grounded. Any proposed explanation must produce an effect of the observed magnitude and direction without violating established uncertainty bounds. Uncertainty thus becomes a tool for discipline rather than doubt. For 3i Atlas, the outcome of this phase is a refined understanding of reliability. The measurements are not perfect, yet they are consistent enough to support the existence of a small persistent deviation. The uncertainty envelope is well defined, and the deviation sits outside its core. This positioning justifies further investigation while maintaining caution. The role of uncertainty analysis is therefore complete when it has been exhausted as an explanation. It does not eliminate the deviation, but it frames it. The numbers are now accompanied by clearly stated confidence levels. They do not demand extraordinary conclusions, but they resist dismissal. The deviation remains modest in scale, yet it is statistically significant within the context of the data. With uncertainty characterized and bounded, the focus can shift. The refined orbit and quantified confidence provide a stable platform for examining additional influences. The question moving forward is no longer whether the deviation is real within measurement limits, but whether known physical processes acting subtly and persistently can account for it. The groundwork laid by uncertainty analysis ensures that this next step proceeds with restraint clarity and respect for the limits of the data. With uncertainty bounded and the refined orbit established, analysis turns toward gravitational influences beyond the simplest assumptions. Gravity is the dominant force shaping motion in the outer solar system, yet it is not limited to the Sun alone. Every massive body contributes, and at high precision even distant or diffuse sources must be considered. This stage examines whether known gravitational influences acting together could account for the observed deviation without invoking new mechanisms. The primary gravitational source is the Sun, whose mass determines the overall curvature of trajectories. Its value is known with exceptional accuracy, constrained by planetary motions and spacecraft tracking. Small uncertainties in solar mass exist, but their effect on an individual object's acceleration is uniform and symmetric. Adjusting the solar mass within its uncertainty shifts predicted positions in a way that does not match the directional pattern of the residuals. This avenue therefore provides no resolution. The next contributors are the major planets. Jupiter, Saturn, Uranus and Neptune exert gravitational forces that extend far beyond their orbits. These forces are included in standard models using precise planetary ephemerids. The timing and geometry of their influence are well known. For an object far from the planets, their effects are smooth and slowly varying. Close encounters produce sharp changes, but no such encounters are present for 3i Atlas during the observed interval. The deviation does not align with the signature of a planetary perturbation. Planetary masses themselves are considered. Although well measured, they carry small uncertainties. Adjusting these masses within their allowed ranges alters gravitational forces slightly. Sensitivity tests apply these adjustments to assess impact. The resulting changes in predicted motion are orders of magnitude smaller than the observed deviation. Moreover, their spatial pattern differs, failing to reproduce the consistent offset seen in the data. Smaller bodies such as large asteroids or trans-Neptunian objects are also examined. Individually, their masses are negligible compared to the planets. Collectively, they form populations that can influence motion through cumulative effects. However, these effects are usually treated statistically and produce diffuse perturbations rather than coherent trends. Known massive trans-Neptunian objects are included where relevant, yet their contributions remain too small and too localized to explain the deviation. The galactic tide represents a broader gravitational influence. It arises from the combined mass of stars, gas, and dark matter in the Milky Way. At the scale of the outer solar system, the galactic tide produces gentle accelerations that can alter long-term orbital evolution. Its effects are most pronounced on extremely distant objects such as those in the distant cloud of icy bodies surrounding the Sun. For objects at the distance of 3i Atlas, during observation the galactic tide is present but weak. Its direction and magnitude are predictable and included in extended models. Incorporating it changes the refined orbit slightly, but does not remove the residuals. Passing stars can also perturb distant objects. Over long timescales, stellar encounters reshape the outer solar system. These encounters are rare and their effects are localized in time. No known stellar passage coincides with the observation period of 3i Atlas. Even if an unrecorded encounter occurred in the distant past, its influence would manifest as a fixed alteration to the orbit, not as a continuing deviation during current observations. The possibility of an unseen massive object is considered cautiously. Hypotheses involving distant planets or compact masses have been proposed in other contexts to explain clustering in trans-Neptunian orbits. Such objects, if present, would exert gravitational influence over wide regions. However, their existence remains unconfirmed, and any such influence would affect many objects in similar ways. The deviation observed here is specific to 3i Atlas, and does not coincide with broader patterns seen in other bodies. Without corroborating evidence, this explanation remains unsupported. Relativistic gravity is included as a final gravitational consideration. General relativity predicts small corrections to Newtonian motion, especially near massive bodies. These corrections are standard in precise orbit calculations. Their effects are strongest near the Sun and diminish with distance. At the distances involved here, relativistic contributions are extremely small and well characterized. They do not align with the magnitude or direction of the observed deviation. The cumulative assessment of gravitational influences yields a consistent conclusion. Known sources of gravity individually and collectively are insufficient to explain the discrepancy. This conclusion is not reached quickly or lightly. Each influence is examined quantitatively with models adjusted and tested. The failure to account for the deviation is informative. It narrows the range of plausible explanations without asserting that gravity behaves differently than understood. Throughout this process, restraint is maintained. The analysis does not suggest missing physics within gravity itself. The models used are robust and have been validated across countless cases. The deviation is small, and gravity remains overwhelmingly dominant in shaping the object's path. The issue lies not in the foundation but in the details. This stage also reinforces the importance of scale. The forces under consideration are immense, yet the deviation is subtle. The mismatch arises at the level of tiny fractions of total acceleration. Such sensitivity underscores the precision of modern measurement and modelling. It also highlights how small persistent effect can become visible only when dominant forces are well understood and controlled. The gravitational analysis concludes with a refined baseline. All known gravitational influences have been included and tested. Their combined effect defines the best gravitational prediction for the object's motion. This prediction remains close to observation but not identical. The residuals persist, retaining their coherence and magnitude. With gravity exhaustively considered, the path forward becomes clearer. If the deviation is not due to measurement uncertainty or known gravitational effects, attention must turn to other forces that can act on small bodies. These forces are weaker than gravity and often negligible, but over time they can produce measurable changes. Their examination requires a shift in focus from the environment at large to the interaction between the object and its surroundings. This transition does not imply that such forces are responsible, only that they represent the next logical layer of analysis. The outer to inner approach continues moving from the broad gravitational context toward more localized interactions. The groundwork laid by gravitational modeling ensures that any additional effects are evaluated against a solid and comprehensive reference. By the end of this phase, gravity has been accounted for to the fullest extent allowed by current knowledge. The numbers still do not add up completely, but they do so within a narrowed and well-defined space. The deviation stands as a measured difference between reality and a model that includes every major gravitational influence known to act in the outer solar system. The scene is set for examining forces that are smaller in scale, but potentially cumulative in effect, acting quietly alongside gravity without altering its fundamental role. Beyond gravity, motion can be nudged by influences so faint they are usually ignored, yet over vast distances and long spans of time they leave signatures that careful measurement can detect. In the cold outskirts where 3I/Atlas is observed, these forces are subtle, patient and cumulative, and their consideration becomes unavoidable once gravity alone fails to account for the numbers. The role of non-gravitational forces is not to overturn celestial mechanics, but to refine it to acknowledge that small bodies are not ideal points moving through a vacuum, but physical objects with surfaces, temperatures, and interactions with light. In this region of space, sunlight is weak, but it is not absent, and even a diluted photon carries momentum. Radiation pressure. The gentle push exerted by sunlight acts continuously on exposed surfaces. For a large asteroid, its effect is negligible. For a small, irregular body with low mass, it can introduce measurable acceleration. The direction of this push is predictable, always away from the sun, but its magnitude depends on properties that are difficult to know: surface area, albedo texture, and orientation. If 3I/Atlas is elongated, tumbling or unusually reflective radiation pressure could bias its trajectory just enough to skew orbital fits. Yet when models apply realistic values, the observed deviation still strains the limits of what radiation pressure alone can explain. Another candidate arises from heat itself. As sunlight warms, a surface-absorbed energy is later re-emitted as infrared radiation. This re-emission is not perfectly symmetrical, especially for rotating bodies, and it produces a tiny recoil known as the Yarkovsky effect. Over millions of years, the Yarkovsky effect can shift asteroid orbits measurably, especially for kilometer-scale objects in the inner solar system. At greater distances, the effect weakens sharply as solar heating declines. For 3 I/Atlas, the expected Yarkovsky acceleration is vanishingly small, yet when uncertainty bars tighten, even such a whisper of force must be tested and ruled in or out. More compelling is the phenomenon historically associated with comets outgassing. As volatile ices warm, they sublimate, releasing gas and entrained dust in jets that act like thrusters. These jets are often uneven, emerging from fractures or sunlit regions, producing accelerations that vary with rotation and orientation. Classical comets display obvious comae and tails betraying this activity, but not all outgassing announces itself so clearly. Some objects release gas at rates too low to form visible features, yet sufficient to alter motion. Carbon monoxide and carbon dioxide can sublimate at temperatures far below that required for water ice, making distant low-level activity possible even where sunlight is weak. If 3 I/Atlas carries such volatiles beneath a darkened crust, it could be experiencing a form of stealth, outgassing, pushing gently but persistently. The difficulty lies in confirmation. Spectroscopic searches may fail to detect gas if production rates are low or if geometry is unfavorable. Dust release might be minimal or composed of particles too large or too sparse to scatter detectable light. In such cases, motion becomes the primary clue, a kind of indirect spectroscopy, where force is inferred from trajectory rather than emission lines. This approach demands extreme care. Non-gravitational acceleration must be distinguished from systematic errors, from catalogue biases, and from unmodelled gravitational influences. Astronomers fit additional parameters to orbital solutions, allowing for small accelerations in radial transverse or normal directions relative to the orbit. When these parameters improve the fit significantly, they hint at physical processes acting on the body. For 3 I/Atlas, the inclusion of non-gravitational terms reduces residuals, but the required acceleration shows an unusual orientation not neatly aligned with the Sun-object line, as simple outgassing would suggest. This peculiarity invites further scrutiny. One possibility is that rotation complicates the picture. A rapidly tumbling object averages out jet directions over time, producing an effective acceleration that is offset from instantaneous emission. Another is that surface properties vary strongly with patches of activity turning on and off as illumination changes. The geometry of spin unknown and unconstrained becomes a critical variable. Beyond these familiar forces, there are more exotic yet still physical effects to consider. Interaction with the solar wind, a stream of charged particles flowing outward from the Sun can exert pressure and induce electric charging on small bodies. For most asteroids, this interaction is negligible, but for very low-mass porous or dusty objects, electromagnetic effects can subtly modify motion. Photoelectric charging plasma drag and Lorentz forces have been studied primarily for dust grains, not kilometre-scale bodies, yet the boundary between regimes is not sharply defined when properties are uncertain. If 3 I/Atlas possesses an unusually low density or a highly porous structure, Its response to the interplanetary environment could differ from expectations. Still, calculations suggest that such effects remain orders of magnitude too small, unless the object is extraordinarily atypical. The careful weighing of these possibilities reflect a broader principle in planetary science. Extraordinary claims demand ordinary explanations tested exhaustively before more radical ones are entertained. Non-gravitational forces provide a rich toolkit for explaining deviations without invoking unknown physics. They remind observers that motion is the integrated outcome of many interactions, some visible, some hidden. Yet they also impose discipline. Each proposed force must be consistent with thermodynamics, material science, and observational limits. For instance, sustained outgassing implies a reservoir of volatiles. That reservoir should over time alter surface appearance or mass. Radiation pressure effects scale with area to mass ratio. Extreme values would imply a structure unlike most known asteroids. Thus, dynamics feeds back into physical inference. The numbers do not merely describe motion, they constrain what the object can be. As the analysis continues, astronomers compare 3I/Atlas with known cases where non-gravitational forces dominate. Interstellar visitor 1I/Oumuamua famously exhibited non-gravitational acceleration without a visible coma sparking debate over its nature. Subsequent studies show that hydrogen or nitrogen ice or dust-free outgassing could in principle explain its behavior, though each hypothesis carried implications that remain debated. The lesson is not that anomalies demand sensational answers, but that small bodies can behave in ways that stretch existing categories. 3. I/Atlas enters this context not as a repetition, but as a new data point with its own parameters and uncertainties. Its deviation invites comparison, but resists easy analogy. In the quiet accounting of forces, scientists proceed incrementally. They test radiation pressure, reject what is insufficient, adjust outgas in models, explore rotation states, and refine physical assumptions. Each iteration narrows the space of possibilities. The process is slow, almost meditative, and it unfolds far from headlines. What matters is not the drama of deviation, but the consistency of explanation. Non-gravitational forces sit at the intersection of physics and observation, where theory must bow to measurement, and measurement must be interpreted with humility. In this space, 3I/Atlas continues on its path, influenced by forces too small to feel, yet large enough to matter. The numbers, when read carefully, do not accuse nature of error. They ask observers to listen more closely to the quiet voices that guide small bodies through the dark. Understanding motion ultimately requires understanding the thing that moves. Once non-gravitational forces are seriously considered, attention shifts from equations back to the object itself, to its size, mass structure and surface, because these properties determine how strongly faint forces can act. 3I/Atlas is distant and unresolved, appearing only as a moving point of light against a background of stars, yet even such limited information carries constraints. Brightness variation over time and color indices allow astronomers to infer ranges rather than certainties, sketching a physical portrait that remains blurred but not blank. From observed magnitude and assumed reflectivity, estimates of size emerge. If the surface reflects sunlight efficiently, the object could be relatively small. If it is dark, absorbing most incident light, it must be larger to appear as bright as it does. Most small bodies in the outer solar system are dark-coated in complex organic compounds, altered by radiation over long periods, and if 3I/Atlas follows this pattern, its diameter likely lies in the range of hundreds of meters to a few kilometers. This range matters profoundly. Mass scales with volume while non-gravitational forces scale with surface area. A smaller lower mass object is far more susceptible to gentle pushes, whereas a larger body resists them. Thus, size estimates feed directly back into the plausibility of radiation pressure or outgassing as explanations for the observed deviation. Light curves provide another window. As 3I/Atlas rotates, its brightness may vary, revealing clues about shape and spin state. Elongated or irregular bodies produce larger brightness variations than near-spherical ones. Preliminary measurements suggest modest variability, hinting at some asymmetry, but not the extreme elongation seen in certain past interstellar visitors. Rotation period, however, remains uncertain. A slow rotator would respond differently to heating than a fast one. Rapid rotation tends to distribute solar energy more evenly, suppressing localized jets, while slow rotation allows strong day-night contrasts that can drive asymmetric activity. Without a well-constrained spin period, models of thermal behavior remain provisional, yet the range of possibilities can still be explored. Color measurements add another layer. The spectrum of reflected light indicates surface composition at a coarse level. Redder colors are associated with organic rich radiation-processed surfaces common among trans-Neptunian objects, while more neutral colors suggest fresher ice or rock. 3I/Atlas appears neither extremely red nor unusually neutral, placing it within the broad diversity of known small bodies, but not firmly within any single class. This ambiguity again widens the space of acceptable physical models. Density is perhaps the most elusive parameter. Without a resolved shape or a measured mass density must be inferred indirectly. If non-gravitational acceleration is confirmed at a certain level, density cannot exceed a corresponding upper limit. A denser object would simply be too massive to be pushed so noticeably. This logic was applied famously to earlier anomalous objects, leading to suggestions of unusually low density or high porosity. For 3I/Atlas, similar reasoning implies that if outgassing or radiation pressure is responsible, the object must be relatively lightweight for its size. That could indicate a porous rubble pile structure, or a body rich in ices with internal voids. Such structures are not exotic in the solar system. Comets are known to have low densities, sometimes comparable to loosely packed snow. The question is not whether such an object can exist, but whether its other observed properties align with that picture. Surface activity, or the lack thereof, complicates matters. No obvious coma or tail has been detected even in deep imaging. This absence does not rule out activity but constrains its nature. Any gas production must be weak dust, poor, or composed of volatiles that do not efficiently drag dust along. Carbon monoxide and carbon dioxide sublimation can occur without dramatic dust release, especially if dust grains are large or bound by cohesive forces. Alternatively, activity could be episodic, occurring in brief bursts that escape detection between observations. In this case, the physical surface would be patchy, with isolated active regions embedded in an otherwise inert crust. Thermal modeling explores how such a surface would behave. At large heliocentric distances, equilibrium temperatures are low, but subsurface layers can retain primordial ices insulated by a refractory mantle. As the object approaches the sun, heat slowly diffuses inward. If cracks or vents connect volatile layers to the surface, gas can escape in narrow jets. The timing and strength of these jets depend on conductivity, layering, and rotation. For 3I/Atlas, the deviation in motion could correspond to such delayed directional outgassing, even if visual signatures remain faint. Each assumption about internal structure shifts predicted behavior, illustrating how dynamics and physical modeling intertwine. Another consideration is evolutionary history. If 3I/Atlas originated outside the solar system, its surface may have been processed by interstellar radiation for millions or billions of years before arrival. This exposure can alter chemistry, harden surfaces, and deplete the most volatile components. An interstellar object might therefore appear less active than a native comet at similar distances, yet still harbour enough volatiles to produce subtle forces. Conversely, if the object formed within the solar system and was later ejected and returned, its history would differ, and its composition might more closely resemble known populations. Distinguishing these scenarios from limited data is challenging, but physical characteristics provide hints. Extreme porosity, unusual colour, or unexpected volatility patterns could favour one origin over another. Importantly, none of these interpretations require abandoning known physics. They require only that small bodies occupy a broader range of physical states than neatly labelled categories suggest. The term asteroid or comet becomes a convenience rather than a strict definition. 3I/Atlas may sit in the continuum between possessing traits of both. This liminal status is precisely where non-gravitational effects become diagnostically powerful. By constraining how the object responds to light and heat, astronomers back out properties that would otherwise remain hidden. As observational campaigns continue, each new data point refines the portrait. A slight change in brightness trend may hint at emerging activity. A better light curve may narrow rotation period estimates. Improved astrometry tightens acceleration limits, feeding back into density constraints. The process is iterative and cumulative. No single observation resolves the mystery, but together they corral uncertainty. The physical nature of 3I/Atlas thus emerges not as a fixed description, but as a probabilistic envelope shaped by consistency between motion, light, and theory. In this careful reconstruction, restraint is essential. It is tempting to let anomaly inflate into speculation, yet the discipline of planetary science lies in letting the object speak through numbers. The deviation in motion demands explanation, but the explanation must fit within the quiet material reality of a small body moving through space. Whatever 3I/Atlas ultimately proves to be its physical nature will be revealed not by a single dramatic feature, but by the coherence of many modest clues, each reinforcing the others until the picture sharpens enough to stand on its own. Placing 3I/Atlas in context requires looking outward again, not in space, but in classification, comparing it with the very small set of objects that have entered the solar system from beyond. Only a few interstellar visitors have been confidently identified, and each arrived with its own combination of motion, brightness, and physical ambiguity. These precedents do not form a neat template, yet they define boundaries of what has already been observed and modelled within established physics. By examining similarities and differences, astronomers test whether the behaviour of 3I/Atlas fits within this emerging, still sparse category, or whether it extends beyond it. The first confirmed interstellar object revealed itself primarily through its trajectory. Its hyperbolic path showed that it was not bound to the Sun, and its speed far exceeded that of typical solar system bodies at comparable distances. Its physical appearance was puzzling: no obvious coma, modest brightness, and light curve variations suggesting an unusual shape. Most striking was the detection of non-gravitational acceleration without accompanying visible outgassing. This combination forced scientists to revisit assumptions about surface composition and mass, ultimately concluding that subtle, possibly volatile-driven forces could act without producing a classic cometary display. The second confirmed interstellar visitor contrasted sharply. It displayed a clear coma and tail unambiguously comet-like, with gas emissions directly detected. Its motion largely followed gravitational expectations with only minor non-gravitational corrections typical of active comets. Its behavior reassured researchers that interstellar objects need not be exotic. Some may closely resemble familiar solar system comets, differing mainly in origin rather than nature. Together, these two cases established a wide behavioral range from apparently inert yet accelerating bodies to visibly active and dynamically conventional ones. Against this backdrop, 3 I/Atlas occupies an intermediate and still uncertain position. Its inbound velocity and trajectory mark it as unbound, aligning it with the interstellar category in dynamical terms. Its brightness and lack of obvious activity, however, do not immediately place it alongside the clearly active visitor, nor does its acceleration pattern exactly mirror the earlier, more enigmatic case. Instead, it seems to borrow elements from both. The deviations in its motion are subtle, emerging only after careful accumulation of data, and they do not yet demand extreme explanations. This moderation is important. It suggests that interstellar objects may populate a continuum of behaviors rather than clustering at extremes. The solar system has likely been visited by many such bodies in the past, most passing unnoticed, because they behave too much like ordinary comets or asteroids to stand out. Only with improved surveys have the outliers become visible. Comparing physical properties deepens this view. Estimated sizes of known interstellar objects span a range similar to that inferred for 3 I/Atlas. None are large, all are small enough that surface forces matter. Color measurements also overlap. The diversity seen among trans-Neptunian objects within the solar system appears mirrored among these visitors, hinting that planet formation processes elsewhere produce familiar materials. There is no clear evidence that interstellar space breeds fundamentally different small bodies. Instead, it seems to sample the same spectrum of icy rocky and organic rich compositions already known. This similarity reinforces the idea that deviations in motion arise not from alien physics, but from familiar processes acting in unfamiliar combinations. One point of contrast lies in activity thresholds. The clearly active interstellar comet displayed gas emission at distances where solar system comets often do the same, driven by volatile ices. The more inert visitor showed no such signs even when acceleration was present. 3 I/Atlas observed at comparable or greater distances shows no strong activity, aligning it more closely with the latter case. Yet its acceleration, if confirmed, appears weaker. This difference could reflect size, composition, or evolutionary history. A slightly larger body with similar surface properties would show reduced acceleration. Alternatively, partial depletion of volatiles could suppress both activity and force. These are incremental differences, not categorical ones, reinforcing the sense of a gradient rather than a dichotomy. Temporal coverage also matters. Earlier interstellar objects were detected relatively late, limiting observation windows. For 3 I/Atlas, detection occurs earlier, along its path, providing more time to watch how its behavior evolves. This extended baseline allows more sensitive tests of models. If activity turns on gradually, it may be caught. If acceleration changes with distance, the trend can be measured. Comparisons therefore remain provisional, subject to revision as more data accumulate. It is also important to compare 3I/Atlas with extreme solar system objects, not only with interstellar ones. Some long-period comets display weak activity and unusual accelerations. Certain near-Earth asteroids show subtle non-gravitational forces due to thermal re-radiation. These native examples demonstrate that anomalies are not exclusive to interstellar origin. By situating 3I/Atlas among both groups, astronomers assess whether its behavior truly stands apart or merely occupies an undersampled corner of known parameter space. So far, it does not clearly violate boundaries established by solar system bodies, though its combination of properties remains uncommon. The small sample size of interstellar objects limits statistical inference. With only a handful of examples, patterns may be misleading. Each new detection carries disproportionate weight-shaping expectations that may later need adjustment. For this reason, restraint is emphasized in comparative analysis. Similarity does not prove shared origin beyond dynamics, and difference does not imply exotic nature. The role of comparison is to constrain, not to conclude. For 3I/Atlas, the comparison suggests plausibility. Its motion and physical hints fit within the envelope defined by earlier visitors when uncertainties are properly accounted for. The numbers do not add up only in the sense that simple gravitational models fall short, not in the sense that known physics fails. This distinction is crucial. By framing 3I/Atlas alongside its predecessors, scientists avoid isolating it as an anomaly unto itself. Instead, it becomes part of an emerging population, one that challenges observational capabilities more than theoretical foundations. As detection rates increase, the category of interstellar objects will likely expand and diversify. Some will be active, some inert, some subtly accelerating, others strictly gravitational. 3I/Atlas may eventually appear ordinary within this expanded set. For now, its value lies in extending the comparative range, filling in the space between extremes. Through this comparison, uncertainty is narrowed. Explanations that worked before remain viable, while those that failed are set aside. The object's behavior is not interpreted in isolation, but weighed against what has already been seen to occur naturally. In this slow, cumulative process, understanding advances not through dramatic revelation, but through alignment as each new object is fitted into a growing, still incomplete map of small bodies moving between the stars. By the end of this comparison, 3I/Atlas stands neither as a copy nor as an outlier, but as another data point quietly insisting that the solar system is open, permeable, and continuously sampling the debris of distant planetary systems. Once comparison establishes that 3I/Atlas does not sit outside the known range of small body behavior, attention turns inward again toward explanation through modeling. Modeling is the quiet workhorse of planetary science, translating physical assumptions into predicted motion, and then testing those predictions against observation. For 3I/Atlas, the central task is not to invent new forces, but to examine how known forces combine under plausible conditions. The apparent deviation from a purely gravitational trajectory provides a constraint, not a mystery in itself. Any acceptable model must reproduce the measured positions over time within observational uncertainty, while remaining consistent with realistic physical properties. The simplest model begins with gravity alone. The Sun dominates with minor contributions from planets. This baseline fits most of the data, but leaves small systematic residuals. These residuals are not random scatter. They trend in a way that suggests an additional acceleration component. Modelling proceeds by asking what magnitude and direction of extra acceleration would minimize these residuals. The result is typically a small continuous force acting roughly away from the Sun. This direction immediately narrows the field of candidates. Forces aligned radially outward point toward mechanisms tied to solar radiation or heating rather than toward random external perturbations. Radiation pressure is the first mechanism tested. It arises from momentum transfer when sunlight strikes and reflects from a surface. Its strength depends on surface area reflectivity and mass. Modelers assign a plausible size and albedo to 3I/Atlas and calculate the resulting acceleration. If the object is very small or unusually reflective, radiation pressure could be significant. However, for sizes inferred from brightness, assuming typical dark surfaces, radiation pressure alone falls short. It may contribute but cannot fully account for the observed deviation, unless density is implausibly low or reflectivity unrealistically high. This outcome does not eliminate radiation pressure but relegates it to a secondary role in most scenarios. Attention then shifts to outgassing, the release of gas from volatile materials warmed by the Sun. In models, outgassing is represented as a force whose magnitude depends on gas production rate, and whose direction depends on the geometry of active regions. The simplest assumption is isotropic outgassing, where gas escapes evenly from all sunlit areas. This produces little net force as pushes cancel out. To generate acceleration activity must be asymmetric. Models therefore introduce localized vents or jets. Parameters include the location of active regions, their efficiency, and how activity varies with distance from the Sun. Even modest gas production, if concentrated, can yield measurable acceleration for a low-mass object. Importantly, such activity need not produce a visible coma if dust coupling is weak. Models show that gas-only outflow can remain optically subtle while still dynamically effective. Thermal lag is incorporated next. Heating does not instantaneously translate into outgassing. Subsurface layers warm gradually. This delay shifts the direction of the force relative to the Sun object line, potentially explaining deviations that are not perfectly radial. By adjusting thermal inertia and rotation rate, models can reproduce a range of acceleration vectors consistent with observations. These parameters are not arbitrary. They are bounded by laboratory measurements of icy materials and by observations of comets. Within these bounds, acceptable solutions exist. Another modelled mechanism is the Yarkovsky effect, a thermal recoil force arising from asymmetric re-radiation of absorbed sunlight. It is well documented for asteroids and depends on rotation, thermal properties, and size. For 3I/Atlas models indicate that this effect is likely small but not negligible. Over long timescales it can alter orbits, but over the limited observation window its contribution may be comparable to measurement uncertainty. Still including it improves fits marginally and provides a more complete physical picture. Models also test combinations of forces. Real objects are subject to radiation pressure, outgassing, and thermal effects simultaneously. When combined, these forces can mimic a single effective acceleration, making disentanglement challenging. The goal is not to isolate one mechanism definitively, but to determine whether a reasonable combination reproduces the data without contradiction. For 3I/Atlas combined models perform better than any single mechanism alone, suggesting that its behavior arises from the superposition of small effects rather than from a dominant exotic one. Crucially, modelling respects uncertainty. Input parameters are varied within plausible ranges, producing families of solutions rather than a single answer. Some solutions fit slightly better, others slightly worse, but many remain acceptable given current data quality. This ensemble approach avoids overconfidence. It acknowledges that limited observations cannot pin down all variables, especially those related to internal structure. The models therefore map a region of parameter space where 3i/Atlas can reside comfortably. External influences are also tested. Passing stars, unseen massive objects, or drag from interplanetary material are considered. These forces are found to be negligible at the object's location and velocity. Including them does not improve fits and often worsens them. Their exclusion is not an assumption, but a result. By systematically testing and discarding these possibilities, modelling narrows focus to the forces that matter. An important aspect of modelling is falsifiability. Good models make predictions that can be checked as new data arrive. For example, if outgassing drives acceleration, its magnitude should change predictably with distance from the Sun. If radiation pressure dominates, acceleration should scale with the inverse square of distance and remain aligned with sunlight. Modelers compare these predicted trends with ongoing observations. Early indications suggest some distance dependence, but uncertainties remain large. The process is iterative. Each new measurement updates model weights, strengthening some scenarios and weakening others. Throughout this work, language remains careful. Models do not claim what 3i/Atlas is. They state what it could be without violating known physics. This restraint reflects experience. Past anomalies have often resolved into ordinary explanations once data improved. Modelling serves as a disciplined check against narrative temptation. It keeps interpretation anchored to equations and measurements rather than to surprise. For 3i/Atlas modelling demonstrates sufficiency. Known forces applied to a plausible object can account for the deviation. The numbers add up within uncertainty when complexity is allowed to enter gradually. This does not eliminate mystery, but it relocates it. The unknowns lie in details of structure and composition, not in the fundamental laws governing motion. In this sense, modelling completes a loop. Starting from observation, moving through comparison, and returning to physics, it shows that the system remains closed. There is no need to open it to speculative mechanisms. The object behaves as a small body should given a particular set of properties that remain to be refined. As observation continues, models will sharpen. Some parameters will converge, others will be ruled out. Until then, modelling stands as a quiet assurance that the deviation of 3i/Atlas is a problem of measurement and material, not of principle. Every model, no matter how carefully constructed, rests on the quality and extent of the data beneath it. For 3i/Atlas, the greatest constraint is not a lack of theoretical tools, but the inherent limits of observation. The object is faint, distant, and fast-moving, and each of these properties narrows what can be known with confidence. Understanding these limits is part of the scientific process, not an admission of failure. It defines where conclusions end and where uncertainty begins, allowing interpretation to remain proportional to evidence. The most fundamental limitation is angular resolution. From Earth-based telescopes, 3i/Atlas appears as a point source. Its physical shape, surface features, and internal structure are entirely unresolved. Even the largest mirrors cannot separate light reflected from different parts of the object. As a result, all physical inferences rely on indirect proxies such as brightness, color, and motion. These proxies are informative but degenerate, meaning that different physical realities can produce similar observational signatures. A small bright object and a larger dark one can look the same. A porous body and a compact one can respond similarly to weak forces if other parameters adjust accordingly. This degeneracy cannot be eliminated without spatial resolution, which is currently unattainable. Photometric data introduce further constraints. Brightness measurements depend on calibration, atmospheric conditions, and background subtraction. Small systematic errors can propagate into size and albedo estimates. Light curves, which might reveal rotation, are often sparsely sampled because observation windows are limited by weather telescope scheduling and the object's position in the sky. As a result, periodicity may be aliased or missed entirely. A rotation period inferred from incomplete coverage may be suggestive rather than definitive. Without a secure spin, state models of thermal behavior remain broad. Spectral data are similarly limited. The object's faintness restricts spectral resolution and signal-to-noise ratio. Only coarse color information is typically available, insufficient to identify specific compounds. Absorption features that would reveal surface ices or minerals are often below detection thresholds. This absence of evidence does not imply absence of material, it reflects instrumental sensitivity. Consequently, compositional interpretations must remain general, framed in terms of classes rather than specific substances. Astrometric precision, while high, by historical standards, also has limits. Position measurements are affected by reference frame accuracy, detector characteristics, and the distribution of background stars. Over short arcs, small errors can masquerade as physical acceleration. Distinguishing between noise and signal requires time. Only by accumulating observations over weeks or months can trends be separated from scatter. For 3I/Atlas, the deviation emerges gradually, becoming apparent only after repeated measurements. Even now, its magnitude and direction carry uncertainty bands. Modelling must therefore accommodate a range of accelerations rather than a single value. Temporal coverage imposes another boundary. Observations capture the object during a specific segment of its trajectory. Behavior outside this window remains unknown. Activity could have occurred earlier at larger distances, leaving no trace. Alternatively, stronger effects may arise later as the object approaches the Sun more closely. Without continuous monitoring across the entire passage, interpretations remain provisional. The object's past before detection and its future after fading from view are inferred rather than observed. Distance itself is a limiting factor. At large heliocentric distances, sunlight is weak, reducing both brightness and thermal response. Subtle forces operate slowly, making their effects harder to measure against background uncertainty. As the object moves inward, signals strengthen, but observation geometry may worsen. Low solar elongation can place the object near the Sun in the sky, limiting ground-based access. Thus, the phase of greatest physical interest may coincide with reduced observability. Instrumental diversity partially mitigates these limits, but introduces its own complexities. Data from different telescopes must be cross-calibrated. Variations in filters, detectors, and reduction pipelines can introduce offsets. Combining such data improves coverage but requires careful statistical treatment. Residual inconsistencies can widen uncertainty rather than narrow it if not properly handled. This is especially relevant when searching for small accelerations that depend on precise positional consistency. Another limit lies in what cannot be measured directly at all. Mass density and internal structure remain inferred quantities. Without gravitational interaction with another body or spacecraft, flyby mass cannot be directly determined. Density estimates depend on assumed size and inferred mass from acceleration modeling compounding uncertainties. Internal layering porosity and volatile distribution are entirely unconstrained observationally. Models explore possibilities, but data do not yet discriminate strongly among them. Even classification as interstellar rests on trajectory determination within uncertainty. While current data strongly support an unbound path, hyperbolicity depends on precise velocity measurement. Small systematic shifts could alter calculated excess velocity slightly, though not enough to change the qualitative conclusion. Still, this reliance on precision highlights how classification itself emerges from data quality. Importantly, these limits are not static. They evolve as observation continues and as instrumentation improves. What is uncertain today may become constrained tomorrow. The role of acknowledging limits is not to halt inquiry, but to guide it. By identifying which parameters dominate uncertainty, scientists prioritize observation strategies. For 3I/Atlas, improving astrometric precision and extending temporal coverage are more valuable than marginal gains in spectral detail. This prioritization reflects an understanding of where data are thin and where they are robust. Within these bounds, conclusions must remain measured. It is accurate to say that the numbers do not fully align with a simple gravitational model. It is also accurate to say that multiple known mechanisms can plausibly account for the discrepancy. What cannot yet be said is which mechanism dominates, or what precise physical structure underlies the behavior. These unanswered questions are not gaps to be filled with speculation, but spaces marked clearly as unresolved. This discipline maintains coherence between observation and explanation. The limits of current data thus serve as a quiet boundary. They prevent overreach and preserve flexibility. As long as 3I/Atlas remains distant and unresolved, its story is necessarily incomplete. Yet incompleteness does not equate to confusion. The data define a constrained region of possibility within which the object moves both physically and conceptually. Recognizing these limits ensures that interpretation remains anchored, allowing future observations to refine rather than overturn what is already known. As uncertainty is mapped and limits are acknowledged, attention moves inward again to the practical response of the scientific community. Continued observation. For an object like 3I/Atlas, understanding does not arrive in a single moment, but accumulates through coordinated patient watching. Observation campaigns are designed not to chase surprise, but to steadily reduce ambiguity, tightening constraints until only a narrow range of explanations remains. This process unfolds quietly across observatories, instruments and months of time guided by priorities set from earlier analysis. The first objective is sustained astrometric tracking. Precise position measurements over long baselines are the most powerful tool for characterizing motion. Each new data point slightly adjusts the calculated orbit, refining estimates of velocity and acceleration. As time passes, random errors average out while systematic trends persist. For 3I/Atlas, continued tracking allows scientists to determine whether the detected deviation remains constant, increases, decreases, or changes direction. Each pattern would favor different physical mechanisms. Observatories with wide field capability play a key role, repeatedly scanning the sky and recovering the object even as it fades or moves into crowded star fields. Alongside wide-field surveys, targeted follow-up observations provide depth. Larger telescopes are scheduled to observe 3 I/Atlas during optimal windows, focusing on higher signal-to-noise measurements. These observations refine brightness estimates and search for subtle changes over time. Even the absence of change is informative. A stable brightness trend across varying distances constrains activity models, ruling out scenarios that predict strong variability. Conversely, a gradual brightening or unexpected dip could signal emerging processes on or beneath the surface. Photometric monitoring is therefore maintained with consistency rather than intensity, favoring regular cadence over sporadic deep imaging. Spectroscopic campaigns, though challenging due to faintness, are also pursued. Sensitive instruments attempt to detect gas emission lines that would reveal active outgassing. These efforts often yield non-detections, yet such results still narrow possibilities. Upper limits on gas production rates feed directly into dynamical models restricting how much force outgassing can provide. Over time, repeated attempts across different wavelengths build confidence that activity if present lies below certain thresholds. This cumulative approach transforms silence into constraint. Observation geometry adds complexity. As 3 I/Atlas moves along its trajectory, its position relative to Earth and the Sun changes. Some configurations favor astrometry, others photometry, others spectroscopy. Campaigns adapt, shifting emphasis as geometry evolves. When the object approaches low solar elongation, ground-based observation becomes difficult. Space-based assets may then offer advantages free from atmospheric interference and able to observe closer to the Sun. Scheduling such observations requires long-term planning and justification, informed by the object's potential to clarify broader questions about interstellar populations. International collaboration becomes essential. No single observatory can maintain continuous coverage. Data are shared across institutions, merged into common databases and analyzed jointly. Standardized reduction pipelines help minimize systematic differences. This collaborative framework ensures that the observational record is as coherent as possible, reducing the risk that apparent anomalies arise from mismatched datasets rather than from physical reality. In this sense, observation campaigns are as much about coordination as about photons. Time itself is an observational parameter. Some forces reveal themselves only over extended intervals. The Yarkovsky effect, for example, accumulates slowly. Thermal lag effects may change as surface layers evolve. By observing 3 I/Atlas over months rather than weeks, campaigns allow these gradual processes to imprint themselves on the trajectory. Even if the object remains faint and unremarkable in appearance, its motion becomes a record of its interaction with sunlight and space. Each additional week of data sharpens this record. There's also a broader motivation behind these campaigns. 3 I/Atlas is not studied solely for its own sake. It serves as a test case for how future interstellar objects will be handled. Observation strategies refined now will be applied again when the next visitor is detected. Decisions about cadence, instrument choice, and data sharing are informed by lessons learned here. In this way, the campaign contributes to methodological knowledge as much as to object-specific understanding. Limits remain. Observations cannot reveal internal structure directly. They cannot measure mass or density outright. They cannot watch the object's past or future beyond observational reach. Campaigns operate within these boundaries, aiming not to eliminate uncertainty entirely, but to compress it. The goal is convergence. As data accumulates, some models will cease to fit. Others will remain viable. The space of explanation shrinks. Importantly, campaigns are designed to avoid bias. Observers do not seek confirmation of a favoured hypothesis, but collect data that discriminate among alternatives. This neutrality is enforced through blind analysis techniques and through the separation of data acquisition from interpretation. By the time results are discussed, the data already exist, limiting the influence of expectation. As the object continues its passage, there will be a point when observations naturally wind down. The object will fade, recede, or move into unfavourable geometry. Campaigns anticipate this front-loading critical measurements and accepting that the window is finite. The end of observation does not mark the end of analysis. Archived data will continue to be re-examined as models improve and as new interstellar objects provide comparative context. In this extended life of the data 3, I/Atlas will remain relevant even after it is no longer visible. Through these ongoing campaigns, knowledge advances incrementally. No single observation resolves the deviation. Instead, understanding emerges from persistence. Each measurement is small, each improvement modest, yet together they transform uncertainty into structure. The deviation that first appeared as a numerical inconsistency becomes, through continued watching, a constrained phenomenon tied to material properties and known forces. Observation campaigns thus serve as the bridge between mystery and explanation, operating not through dramatic discovery, but through steady accumulation, until what once seemed not to add up settles quietly into coherence. After modelling, comparison, and extended observation, what remains is not a solution but a boundary. For 3 I/Atlas, uncertainty is not a flaw in the process, but the natural residue left when data physics and time intersect. The object's behaviour is now constrained within a narrower corridor than when it was first detected, yet that corridor has not collapsed to a single line. Understanding what remains uncertain clarifies both how far knowledge has progressed and where it necessarily stops. The most persistent uncertainty lies in physical structure. Size estimates remain indirect, derived from brightness, combined with assumed reflectivity. Without direct imaging, reflectivity itself cannot be measured, only bracketed. As a result, size and mass remain correlated unknowns. A smaller, denser body and a larger, more porous one can still satisfy current observational constraints. This ambiguity propagates into every dynamical interpretation, because susceptibility to non-gravitational forces depends critically on mass. Until this degeneracy is broken, density remains a range rather than a value. Closely tied to structure is composition. No definitive spectral signatures have been detected. Surface materials are inferred statistically, not identified. Volatile content in particular remains uncertain. If gas production drives part of the observed deviation, the identity and distribution of those volatiles matter. Carbon monoxide, carbon dioxide, or other ices would sublimate at different distances and produce different force profiles. Current data cannot distinguish among these possibilities. The absence of detected gas lines only sets upper limits, leaving open the question of whether weak dust-poor outgassing is present. Rotation state is another unresolved factor. Light curve data suggest variability but do not yet yield a unique rotation period or axis orientation. Without this information, models of thermal response remain broad. Rotation governs how heat is distributed across the surface and how any resulting forces average over time. A slow rotator with localized activity behaves differently from a fast rotator with more uniform heating. Both scenarios remain compatible with the data. The exact magnitude and time dependence of the non-gravitational acceleration also remain uncertain. While deviations from a purely gravitational orbit are supported statistically, their precise form depends on continued astrometric refinement. Small systematic errors could slightly alter inferred acceleration vectors. Although unlikely to erase the effect entirely, they could change its interpretation at the margin, shifting weight between competing mechanisms. This sensitivity underscores how close current measurements are to the threshold of detectability. Origin beyond the dynamical classification of interstellar also retains uncertainty. The trajectory indicates that 3I/Atlas is unbound to the Sun, but its deeper history is inaccessible. Whether it formed in a cold outer disk around another star within a dense stellar cluster, or in a quieter planetary system, cannot be determined from present data. Exposure to interstellar radiation collisions and thermal cycling over long timescales leaves signatures that are subtle and overlapping. No single observable provides a timeline of its past. There is also uncertainty in representativeness. With so few confirmed interstellar objects, it is unclear whether 3I/Atlas is typical or exceptional. It may reflect the median properties of such bodies, or it may occupy a tail of the distribution. This distinction matters for broader interpretation. Conclusions drawn from a small sample must remain provisional, aware that future detections may reshape context. The limits of observation impose a final boundary. As the object recedes or becomes geometrically inaccessible, new data will cease. Some questions will remain unanswered, not because they are unimportant, but because the opportunity to answer them has passed. This finite window is a fundamental feature of transient astronomical phenomena. Analysis will continue, models will be refined, but they will work with a fixed data set. What is learned must be extracted from what is already recorded. Importantly, none of these uncertainties undermine the coherence of the current understanding. They define its edges. The deviation in motion is real within measured limits. Known physical processes can plausibly account for it. The object does not require revision of gravitational theory or the introduction of speculative forces. What remains uncertain concerns degree not kind. How porous is the body, not whether porosity exists. How much gas escapes, not whether gas physics applies. How representative the object is, not whether it belongs to the interstellar population. In this sense, uncertainty here is quiet and bounded. It does not point outward toward mystery, but inward toward detail. The remaining unknowns are refinements awaiting either improved instruments or future objects that allow comparison. For now, 3I/Atlas stands as a constrained case study defined as much by what cannot yet be said as by what can. This balance is the natural end state of careful inquiry. When the numbers first appeared not to add up, they signaled tension between observation and expectation. After sustained analysis, that tension resolves into a narrower question, set framed within established physics. What remains uncertain is not the validity of the framework, but the exact placement of this object within it. That uncertainty persists stable and acknowledged as the final region reached in this inward exploration. The motion of 3I/Atlas now fades from analysis into quiet continuity. After measurements, comparisons, and constraints, the object remains what it has always been, a small body moving through space, governed by forces that act gently but persistently. Its path is no longer examined for discrepancy, but held as a record, a sequence of positions and times that capture a brief passage through the solar system. In this final inward step, attention rests not on explanation, but on stability, on what is settled enough to allow the mind to slow. The sun continues to provide light and heat, weakening with distance strengthening as proximity changes indifferent to classification or origin. The object responds according to its material nature, whatever precise form that nature takes. Gravity remains dominant with subtle additions layered quietly on top. Nothing abrupt occurs. There is no moment of resolution, only the gradual narrowing of possibility until motion and matter align comfortably within known bounds. The numbers that once seemed misaligned now rest within tolerances, their differences absorbed into uncertainty rather than contradiction. 3. I/Atlas recedes into the broader population of small bodies distinguished by origin, but not by behavior beyond what physics already allows. Its significance does not depend on novelty, but on participation, on being one instance among many that trace the same laws across different histories. As observation ends, the data remain fixed and complete, awaiting re-examination when context changes or when new visitors arrive to reshape comparison. For now, the object continues outward, leaving behind no trace beyond recorded light and calculated motion. The solar system returns to its usual quiet traffic and attention settles. There is no conclusion to draw, no meaning to assign. The account simply comes to rest, having moved from outer space to inner detail, and finally to stillness where motion continues unobserved and understanding pauses without strain.